Hello, we are going to present the demonstration of our artificial intelligence practicum project. Our project is called Intelligent Mancala. So, what is a Mancala? Mancala is basically a two-player game played around the world where players move stones around a board trying to capture as many stones as possible. Here's a sample of the Mancala board. The board consists of pits, stones, and mancalas. Each player has its own pits and a mancala. A player selects a pit that contains more than one stone, and the stones are distributed among the all other pits, moving counterclockwise around the board, starting with the pit immediately next to the chosen pit, including the mancala, but not the opponent's mancala, until the player has run out of stones. There are three rules of mancala. Rule number 1, if player's last stone ends in its mancala, it gets a free turn. For example, here we can see if player 1 chooses pit number 1, which has 3 stones, the last stone will end up in its mancala. Therefore, player 1 gets a free turn. Rule number 2, if player's last stone ends in its empty pit, it can steal the opponent's stones. Here, we see that for player 1, in pit number 1, it has 1 stone. So when player 1 picks the pit number 1, the last stone ends in its empty pit. So it captures all the opponent's opposite pit stones. Rule number 3. If there are no stones in either one of the two players' pits, the game is over. For example, this is almost the end of the game. When player 2 selects pit number 3, there will be no more stones left for player 2. So the game is over and player 1 gets all the remaining stones into its mancala. We implemented two game search algorithms to play mancala intelligently. The selection of next moves in our implementation depends on the evaluation function, which is the number of stones in player's mancala minus the number of stones in the opponent's mancala. In case there's a tie in the evaluation function, we choose the move with the lowest index. Also, the traverse order is from lowest index to highest index. The two algorithms are greedy search and MINIMAX search. Let's try this out.
The first implementation includes the greedy search algorithm. Let us see what happens when a human plays against the greedy AI program and human is the first player. So we select greedy, then we select that human is the first player, and then we select that computer is the second player. Now that we have a setup, we select move 1. Now if we pick move 1, the last stone will end up in our mancala and we'll get a free turn. Now that we have no choice, we'll select a move randomly. Let's say we select move 2. Now it's the AI turn. As we can see in the tree, it evaluates all possible moves and selects the move 1 according to the best evaluation function. After it, it's our move again. Let's pick move 1. When we pick move 1, we can see we can capture the opponent's stones. And then the AI plays its last turn and the game ends. We see that we won against the greedy AI. Now let's see what happens if AI takes the first turn. Again, we select greedy as the algorithm. We select 2 as computer as the first turn and human as the second turn. As it's the first turn for the AI, it again evaluates all possible moves and selects move 1 according to the evaluation function as before. After this, it gets a free turn. Then again, it evaluates all possible moves for the current board position and selects move 2. The tie-breaking rule that we set in the implementation tries to get a free turn as greedily as possible. Now let's see what happens if a greedy AI program plays against itself. Let's run it. We see that player 1 won the game in just 3 moves and has 14 more stones than the opponent.
Okay, let's now try to play with the other algorithm, which is MINIMAX search. We will let the MINIMAX AI to be the first player now. Select 2 for the MINIMAX algorithm, select AI as the first player, and human as the second player. Here, the AI program first builds a tree of depth 2, where the nodes are maximizer and minimizer at depth 0 and 1 respectively. From the figure, we can see the leaf nodes that have negative evaluation function because it is the opponent's turn. So, we have to revert the sign of the value to take into account the minimization for AI. After the tree is built, it evaluates the leaf nodes according to the min-max rules. Also, we see at the minimizer, if it takes move 1, the AI gets a free turn. So, this has to be included also in the minimizer levels. Now, we see the evaluation function values are being pushed to the upper levels according to the minimax rule, and AI select the move 1 as the root node is the maximizer. Let's continue the game a little bit. As we can see now, the AI won the game this time. It's harder to beat Minimax AI in this game compared to Greedy. Let's see what happened when a Minimax plays against itself. We observe that player 2 won in 4 moves, and the difference is just 2 stones because both of the players played optimally.
Let's look at the various findings. First is the greedy search findings. In our experiment of a play of a greedy versus greedy, we observe that player 1 is most likely to win the game regardless of the number of pits and the stones in the game. We also found that player 1 wins with a huge margin. The findings have been tabulated on the slide. Next is the minimax findings. In contrast to the greedy algorithm, it was interesting to find that using minimax for the same parameter settings, player 1 is not as likely to win as in greedy search. Also, the margin is now less because both of the players play optimally. Hope you enjoyed our video. Thank you.